Okay, good. And it's a keynote. Huh? What is this? One moment. I in Cosville, in my Cosville, I uploaded the slide. So please check it. Okay. Wow. If you have any question, yeah, people on Zoom, just raise your hand and ask me a question. It's okay. If not, we're going to move to the next topic. So previously we learned how to formulate the optimization problem, right? Though most of the problem we formulate are linear programming or mixed integer linear programming, okay? But you have idea, right? If the problem is not linear, of course you can formulate it as a nonlinear, right? Linear or nonlinear, it's okay. But I am warning you that nonlinear is not that easy. Okay? Nonlinear programming is not straightforward. It needs special treatment. So now, wow, previously we use a commercial tool, well, the tool we have, right? The solver we have. From now on, we're going to learn how to, what's it? How to treat the problem, how to solve the problem, okay? And by learning all these things, okay, you, in the future, of course, you know how each algorithm works, and also how, well, you know how to develop new algorithm. Even new algorithm is possible because those algorithm use a piece of, what's it, idea from what we learn, what we're going to learn. Okay, so the topic we're going to discuss today is a classical optimization technique, right? And it includes, the first topic is optimality conditions, okay? For example, if you know the surface, I mean the objective function, how can we make sure that this point is optimum point, okay? How to define the optimum point. So we have to distinguish between local optimum and global optimum. The definition is totally different. And the next thing is necessary condition for the local optimum. Okay. Normally we don't, yeah, later I will tell you the difference between local optimum and global optimum. Okay. You will learn about necessary condition and sufficient condition to define the local optimum point. Okay. And the next thing is positive definite and negative definite. Do you know what I mean? The positive definite, negative definite. I should put metrics here, positive definite matrix and negative definite matrix, okay? This is a property of matrix, okay? And we use that property in multiple variables, multivariables optimization. We use this property to define the maximum and minimum, okay? It's related to sufficient condition in case of multivariable, okay? Then we move to optimization with equality constraint. Because the first few topics we discuss here is a condition to determine the local optimum, okay? Without constraint. But if we are handling, if we want to handle constraint, how we incorporate those constraints to the objective function and how it affects the condition, the optimum condition. Okay. And then while the classical way to handle equality constraint is Lagrange multiplier. Okay. Later you will learn Lagrange method. Later means today. Okay. And the next one is Kuhn-Tucker conditions. For Kuhn-Tucker conditions, it's the condition to handle inequality constraint. Okay, this one equality constraint, but this one is inequality constraint. Okay, and the next one is invisible text here. Okay, it's convexity. It's really important, but I don't know why it's disappear, but it's all right. We're going to talk about convexity. Okay, and how to define, to check the convexity of set, convex set, and also convex function. Okay, ready? Then we go from the idea first. Imagine that, well, if we consider the objective function, if our objective function is linear, okay, consider the single variable first. This is our decision variable. We have only one decision variable. Okay. So I should move my cursor here. You can see it, right? And people in the Zoom can see it also. Okay. So we go this way. You see that this axis is objective function. Okay. And because our objective function is linear, you go this way. Okay. For this function, it's increasing, right? You go this way, is decreasing. Okay. And if this area, I mean this domain, S domain, is the feasible region or feasible domain, you see that is very straightforward, because if you want to maximize this function, okay, the solution is here, right? You know that you go one direction is either maximize or minimize, right? You go this way is minimum, right? You reach minimum. We never have a minimum point or maximum point at the middle, right? Because the function is linear, right? Okay, so it's useless to analyze this because it's straightforward. You know, the optimum always located at the boundary, right? You go either way, left or right, you get minimum or maximum. Never locate in between. Okay, what about nonlinear? If we consider nonlinear function, it can be like this, okay? Different way, but it's all right. It's nonlinear. Then it's possible, right, that we have minimum point or maximum point in between. Okay. For example, in this case, we have minimum here, one minimum is here, one minimum is here, right? We have maximum is here, maximum here, right? So what else? By analyze this function in the feasible domain, okay, in S domain, what else we can extract from this graph? You see that we have two maximum, but these 2 points are maximum in relative to neighbor points, right? For example, this one, this point, you go either way, to left, to the right, the function decrease. Also here, you go either way, the function decrease. So we call it relative maximum. Okay? Or in other words, local maximum. Okay? Okay. So what about this? Well, the same way, we call it local minimum. Okay? Or relative minimum. Okay? But for the whole domain, which point is the maximum? Yeah, at the boundary. At the boundary, but it's not local. Okay? This one is global maximum. All right? Global maximum can be local maximum or not. Okay? So you see that the definition is totally different, right? Between relative and global. Okay? When we say local maximum or minimum, or relative minimum or maximum, we compare that point with neighbor points. Okay? But for global, we compare with all points, all feasible points in the feasible domain. Okay? What about local minimums? I should say local minima here because it's plural, right? We have two minima, in particular, local minima. And one minimum is global minimum. In this case, global minimum is not here. Global minimum is here, right? And you see that local minimum is also, this local minimum, it's also global minimum. Okay? So now you learn the definition of the local minimum or relative minimum. Okay? So this is the definition. A function of one variable, fx, is said to have a relative or local minimum at x star if f x star is lesser or equal f x star plus h. Okay, for all sufficient small positive and negative value of h. We don't care, well, h is positive or negative, okay? And h is a, well, very small amount, very small value, right? We disturb x star with small value and the function, the value of the function increase, right? Okay. So if we go back to this, yeah, consider this part. We have fx star here, right? And the function, the value of the function of x star plus h, no matter h is positive or negative, we increase the function. That means x star is the minimum, right? Local minimum. Because once we disturb it, the value of the function increase. Okay? So the same way, the point x star is called a relative or local maximum if x star is greater or equal if x star plus h. Okay? We define the same way. Okay? This is the definition of local minimum and local maximum. Oh, the title of this slide should be global minimum, global maximum, not local. Okay. If function fx is said to have a global or absolute minimum, at x star if f x star is lesser or equal fx for all possible x in the domain. Okay, so though you don't care about the neighbor points, but we compare for the whole range of the domain. Okay, and similarly, a point x star will be global maximum of fx if x star is greater or equal fx for all x in the domain. Okay, so we have to compare with all possible x, feasible x in the domain. Okay, okay, now consider this. Well, let's say our domain, consider it's from A to B. Okay, so A1, A2, A1 here, A2, A3 are relative minima or local, no, relative maxima or local maxima, right? And A2 is global maximum. Okay, we have B1, B2 as relative minima, and B1 is global minima. Okay, for the right hand side, we have only one local minima and also global minima. Okay, now global minimum, local minimum. Okay, what about local maximum? For the right hand side, we don't have local maximum. We have global maximum, right? Global maximum is here at B. Okay, any questions? Okay, the next topic is necessary condition. So if we have function fx, okay, in the interval, in our domain, interval between A to B, okay, and we know that we have relative minimum at x star, and x star is in, wow, in this range, in the domain, okay. And other important thing is if the derivative exists, okay, we know that at that local minimum or local maximum, the derivative of that point must be 0. Okay? You cannot go opposite way. We start from the definition that we have fx. Fx is in our domain. And in this domain, we have maximum or minimum. Okay? And our function has derivative. That means derivative exists. Okay? And the local maximum or local maximum, local minimum or local maximum must has derivative to be 0, okay, equal 0. So this theorem can be proved even if this is relative maximum or relative minimum, okay. We use the same theorem, but this theorem doesn't say what happens if a minimum or maximum occur at a point where the derivative fail to exist. Okay, if you don't have in this domain between A and B, you don't have derivative. You cannot say anything. Okay, even you have local minimum, But that local minimum maybe, well, the derivative at that point may be not zero, or that does exist. Okay, we go different way. We say that if we have local minimum, okay, and we know that derivative exists for the whole range, at that maximum or minimum must be, the derivative must be zero. Okay, but if you have, if in this domain the derivative does not exist, you cannot say anything about that. Okay, I will read some example about, yeah, this case. And the next one is the theorem does not say what happened if a minimum or maximum occurs at the end point of the interval of the function. Endpoint means A or B, right? Because we consider between A and B. Okay, if minimum occur at A or occur at B, no, you cannot use this theorem to define it, right? Because of what? For the derivative, you have to take limit from both sides, right? But if that point is the end point, you cannot say anything about that because you cannot take derivative from both sides. And the next one is the theorem that does say what happened if a minimum, no. The next one, the theorem that does say that the function necessary will have a minimum or maximum at every point where the derivative is zero. What does it mean? From the theorem, we say that what? We have a function, right, between A and B, and we have local minimum or local maximum between A and B, right? And the derivative exists, then the local maximum must be, the derivative of the local minimum or local maximum must be zero. Okay, but if we know that the derivative is zero, it doesn't mean that that point is minimum or maximum. Okay, consider this case. You see that, for example, we consider this domain. You see that this one, this function, the derivative does not exist here, right? But this one has minimum, local minimum. Okay, so the theorem does not cover this case, right? And it is the, yeah, second one, right? Yeah, the second item, because this point, the derivative does not exist, right? Or this one, you see that in this range, we have the point where the derivative is zero. Okay, when x is zero, the derivative is zero. But this one, this function has no local minimum or local maximum, right? Okay, any question regarding the necessary condition? No. Okay, good. Now we move to the sufficient condition. For sufficient condition, we limit ourselves in a single variable domain. Okay. And well, we have a point x star where if the first order derivative, okay, first f prime and second order derivative equal, well, higher order derivative. Okay, we find the derivative keep increasing the order of the derivative, okay, until we reach the order where, what is it, the derivative, higher order, an order derivative is not zero anymore. Okay, then if x star is a minimum value, if n is even and this value is greater than 0. Okay? Or fx star is a maximum if n is even, okay? And this value, if well, in order of derivative is less than 0. Okay? But if n is odd, fx star is neither a maximum nor a minimum. Okay? Okay, now consider this example. We're going to determine the maximum and minimum values of the function. From fx, right? Fx is 12 x power to 5 minus 45 x power to 4 plus 40 x power to 3 plus 5. Okay, we take first order derivative, second order derivative, third order, fourth order, and fifth order. Okay, and we stop here because beyond this point it becomes 0. Okay, then we find the extreme point first. Okay, we know that the first property is the derivative must be 0, right? But we cannot say it's minimum or maximum or neither minimum or maximum. Okay, we find x first. So we have 3 candidates, 0, 1, and 2. Okay. Now we substitute 0, 1, or 2 back to derivative. Okay. So when x is 0, first order derivative is 0. Second order is still 0. Third order it's not 0 anymore, right? So n, what is n here? N is, pardon? What is n? The highest order. Back to the previous slide is n. N order where the derivative is not 0. What is n? 3. So n is 3. Then what happened to this point? N is odd, right? So it is neither maximum nor minimum. When x is 1, if from 1 is 0, okay? Second order is not 0 anymore. Second order is negative 60. So what is n here? N is 2, okay? So it can be either maximum or maximum. So this is less than 0, right? It's negative. So it should be maximum at this point. When x is 2, if from, okay, first order, it's 0. Second order is positive. So n is 2. It can be maximum or minimum, right? But this is positive, so it should be minimum. Okay? So this is a graph of that function. You see that when x is 0, okay, the maximum order is 3. So it's neither maximum nor maximum at this point. Okay. And we have maximum over there when x is 1 and minimum over here when x is 2. Okay. Any questions? Then we move to multivariables. Let's say, well, we are in dimension problems. X is a point of n order, n dimension. We have x1, x2, x3. Wow, it's different dimension, right? First dimension, second dimension to n dimension. Okay. So if f(x) has an extreme point, either maximum or minimum at x star, okay? If the first partial derivative of f(x) exists at x star, then the derivative, partial derivative of f in each dimension must be equal and equal 0. Okay? We call this vector, okay? You put the derivative of f in respect to each dimension in a vector as a vector. This vector we call Jacobian, okay, J. Okay, and the condition is, this is necessary condition, right? Each element of Jacobian must be 0. Okay, for the minimum or maximum. Okay, if minimum exists, maximum exists, and the derivative exists, right? The Jacobian must be 0. Okay. What about sufficient condition? For sufficient condition, for x star, okay, stationary point x star, to be an extreme point is that the matrix of second partial derivatives. The matrix of partial derivative, we call it H. H is standing for Hessian, okay? We call it Hessian matrix. It is second order, okay? Second order partial derivative, and it is a matrix. I will show you what the structure of that Hessian matrix. Okay, and the condition is if Hessian matrix is positive definite, x star is a relative minimum point. Okay, and if x star Hessian at x star is negative definite, that point is maximum point. Okay, previously, because we work in the single dimension, right? One variable. So we don't have to deal with vector or matrix. But now we move to multi-variables. So instead of one single scalar, the first order becomes Jacobian, and second order becomes Hessian matrix. Okay, so now you have to learn Hessian matrix. And the next thing you have to learn about positive definite and negative definite. Okay. I will tell you briefly about Hessian matrix first, and then positive definite and negative definite. Okay. If you want to learn more, of course, the next semester, there's a course on advanced mathematics. Okay. Okay. So let's say we are in the 2 dimension. Okay. We have x1 and x2, right? You can say x and y. It's all right, but I keep it x1 and x2. Okay. Jacobian is quite straightforward because, yeah, there are 2 dimensions, right? It's partial derivative of f in respect to x1 and respect to x2. Okay. What about Hessian? Hessian is actually matrix. Yeah, but I write this way because this semicolons mean wow. Yeah, move to the next line. Okay, next row. The first element is the second order partial derivative with x1. Okay, x1 and x1. Okay, you got second order, right? But the element at first row, right? 1, 2. Okay, this one is second order of f respect to x1 and x2. Okay. Now we move to the second row. Okay. The first column of second row, it's second order. Of course, everything is every element is second order. Okay. But this one is respect to x2 and x1. Okay. This one. And the element row 2, column 2. Okay. Second row, second column, it's partial derivative of f respect to x2 and x2. Okay. Okay, you see one thing. You see that even in Jacobian, I use semicolon here. That means it's a column vector. Okay. Okay, now one example, this example. Now consider this example. Let me turn off this light. Yes. Our function is x1 cubic x2 plus x2 cube plus 2 x1 square plus 4 of x2 square plus 6. What about Jacobian? Jacobian is straightforward. You take derivative of this one, partial derivative of this one, this function f in respect to x1, right? This one becomes 3 from x1 cube becomes 3x1 square, okay? And from x2 cube, well, it's become 0, right? And the next term is from 2x1 square becomes 4x1, okay? And the other elements, from the first element, x1 cube becomes 0, right? Because we find the derivative respect to x2 direction, okay? And x2 cube becomes 3x2 square. And this term becomes 0. 2x1 square becomes 0, okay? And 4x2 square becomes 8x2, okay? That is, the constant becomes 0, of course. What about Hessian? For Hessian, the first element, you find the derivative of this term, 3x1 square plus 4x1 respect to x1. Okay, so it's 6x1 plus 4, right? And the next element on the second column, partial derivative of this one respect to x2, it becomes 0, right? No x2 there. And the second row, the first one respect to x2, no more x2, so it becomes 0. No, sorry. This term, the second column, second row, okay? But find the derivative of 3x2 square plus 8x2 respect to x1, right? So it becomes 0 because no x1 there. And the last one, we take derivative of 3x2 squared plus 8x2 respect to x2. So we got 6x2 plus 8. Okay, it's a matrix. So this is Jacobian and this is Hessian. All right. So we first thing to do is we find the extreme point first. And we know that for extreme point, the Jacobian must be 0, right? Each element of Jacobian must be 0. So we know 3x1 squared plus 4x1 must be 0. And 3x2 squared plus 8x2 must be 0 also. Okay, put it here. So we have x1 0 or minus 4 over 3. Okay, 1/3 of 4. And for x2 can be 0 or minus 8 over 3. Okay, so how many points do we get? 2 points? No, not 2 points. Not 0 point. 4 points, right? Totally 0, 0, 0, minus 8 over 3, minus 4 over 3, 0, minus 4 over 3, and minus 8 over 3. Okay, totally we have to test 4 extreme points. that yeah, that is the benefit of those who attend on site. Okay, so we have 4 candidates. The first one is 0, 0, right? The next one is 0, minus 8 over 3. Yes, minus 4 over 3 and 0, and minus 4 over 3, minus 8 over 3. Okay, and we have to test all these 4 points. Okay, we have to check the Hessian of each point. So if, yeah, just very simple, and substitute the point to Hessian because we have already derived our Hessian. Okay, so when x is 0, 0, our Hessian is 4, 0, 0, 8, right? If you feel that it's very difficult for you to read this style of writing, you can write by yourself as a metric. Okay, write the whole metric in one line to save the space. Okay, so with the next point, this point, okay, we find the Hessian. You can recheck my calculation. If I did anything wrong, just let me know, okay? Because sometimes I did it wrongly. Also, the third point, we have Hessian, this Hessian, okay? Actually, this problem is quite easy because all these metrics is very easy to recognize the positive definite, negative definite. Why? Because this is the first one for 0, 0, 8. It is a diagonal metric, right? You know diagonal metrics? Yes. Only diagonal, which is not 0, right? The rest of the other points, other elements are 0. Okay, only diagonal. We call diagonal matrix. And each element in the diagonal matrix is positive. So this metric must be positive definite, right? Don't worry, I will tell you how to test it, but for diagonal matrix, you follow this way. It's always correct. Okay? And the next one, this point also, this Hessian. This Hessian also diagonal metric, right? And not all of them are positive or negative. So we cannot say it's positive definite or negative definite because some of them positive, some of them negative. Okay, this one also diagonal, is a mix of negative and positive. Okay, we move to this one, the last one, the diagonal, the element in the diagonal, all negative. Then it must be negative definite. So we know that if this metric is positive definite, this point, the point at 0, 0 must be minimum. And this point must be maximum. Okay, it's negative definite. Okay. But anyway, I will explain more about the positive definite and negative definite. What is the meaning of positive definite and negative definite? If we have metric A is called positive definite if X transpose AX is always greater than 0. No matter what the vector X is, you multiply this way, you got positive scalar, then A is positive definite. And if X transpose AX is less than 0, is negative, A is negative definite. Okay. You can compare it with X square in scalar, X square, right? For metric, of course, you cannot do X square, right? But in matrix, what it's analogous to X square is X transpose X. Okay. And you put A inside that. You see that in case of scalar, if you multiply the negative value to X square, it's always negative, right? And if you multiply positive value to X square, it must be always positive. Okay. And we know that scalar we multiply, it's positive or negative, right? But in case of matrix, if the A you put there and render the result to be positive, A must be positive definite. Or if you put A here, X transpose AX, and it is negative, then A is negative definite. Okay. I tell you what I tell you is the connection between scalar and matrix. Okay. So for example, we have A, this A, minus 4, 0, 0, minus 8. This is diagonal metric, right? We know, suddenly, yeah, that this one is negative definite for sure, right? Because it's diagonal matrix and the elements, all the elements are negative. But I will show you that this definition always hold. Okay. You see that if we choose X as 1, 1, okay, we plug all the X and A and calculate X transpose AX, we got minus 12. Okay. Even we change X to negative, negative, like negative 1, negative 1, minus 1, minus 1 here, the result negative. We choose another X as minus 1, 1. X transpose AX, it's negative. Okay? And the last one, when X is 1 minus 1, X transpose AX, always negative. See? That is the definition. No, this is property. Property of the negative definite. Okay. So if you want to know more about positive definite or negative definite, well, I encourage you to start from reading the eigenvalue problem. Okay. I will briefly explain about this. This is the eigenvalue problem. Okay. And you see that, well, from this property, the property of positive definite, negative definite, you cannot, test this property, test the if A is negative definite by varying the X and then test every point, right? It's impossible to test infinity points because this definition always hold. So you have to test so many points, right? Vector of X, okay? But if you test the eigenvalue, it's much more easier. The positive definite matrix, for the positive definite matrix, all eigenvalues of A must be positive. And for negative definite matrix, all eigenvalues of A must be negative. Just that. Okay? All you have to do is find the eigenvalue. Okay? You don't need eigenvector. You need just eigenvalue. Okay? But you know, any one of you learn advanced mathematics? No? Maybe. Yes, yes, yes. You learned about that already? Yes. I think you use it in ODE. Yes, ODE. System of ODE. You need both eigenvalue and eigenvector. Okay, so for eigenvalue problem, let's say we have A, okay? Always for any A matrix, but A must be square matrix, first thing, okay? But not all A can, well, hold this property, yes, but some of them. A multiply with V vector, okay? If you can multiply this way, of course, you need, appropriate dimension of V, right? For example, if A is 2 by 2, V must be 2 by 1, right? Okay? If not, you cannot multiply it. Okay. And AV equals lambda V, where lambda is scalar. Okay? And V, I use the same symbol, so it must be the same thing. V vector here and V vector here. Okay? You see, if A is 2 by 2, V is 2 by 1, what is the result? Dimension of the result? 2 by 1, right? What about this? V is 2 by 1, right? And V is scalar. What is the result? Dimension of the result? 2 by 1, right? The same dimension, right? So we can compare both sides, right? Yes. So any A, we can decompose it and write as a scalar armed with vector, okay? And we call this lambda as eigenvalue, okay? And V is eigenvector, okay? And you see that this scalar, this lambda eigenvalue, It's scalar, right? But it has the same effect as multiplied by A, which is a matrix, okay? So this is a kind of constant, okay, for that matrix. So I believe, I think you can recognize the word eigen. Eigen is not English. Do you know, well, the originality of eigen, of the word eigen? It sounds like German. It sounds like German. Yeah, you can check the root of that word. There is a kind of constant for the matrix because it has the same effect, right? Okay, so we have A, right? And we want to find the scalar and vector that hold this expression. Yes, it's German, right? Yes. So you move lambda v to the left hand side. So we, yeah, AV minus lambda v equals 0, right? So because we have v, the same v, so we can write this way, A minus lambda, okay? But we cannot subtract lambda from A because lambda is scalar, A is metric. But it is very simple. We times it with identity matrix. I is identity matrix. What is identity matrix? It's diagonal 1, right? Yes, it's diagonal. And the diagonal it's 1, right? So from here, A minus lambda I V equals 0. So we know it's we don't have to say that. We can remove that V, right? So A minus lambda I must be 0. Okay? So if this matrix A minus lambda I is 0, determinant of A minus lambda I must be 0. Okay? So if from this, we can find the lambda. Okay? This is an example in this box on the right hand side. A is minus 2, 3, 1, 0. Then determinant of A minus lambda I is determinant of minus 2 minus lambda, right? The first element. 3, and the second row is 1 and 0 minus lambda, okay? Which is minus lambda, okay. And determinant of this one is lambda times 2 plus lambda minus 3 equals 0, okay? So you do some mathematics here, okay? We got lambda is minus 3 and 1, okay? We have two eigenvalues in this case, okay? The number of eigenvalue must be equal to the dimension of A, always, okay? If our A is 3 by 3, we have 3 eigenvalues, okay? And because we are not going to use eigenvector, okay? I'm not going to talk about eigenvector anymore. But in order to find eigenvector, of course, you have to plug those lambda back to here and find V, okay? Okay, so in this case, in this example, when A is minus 2, 3, 1, 0, you see that A is not defined, right? It's not defined. It's not positive definite. It's not negative definite, right? It's undefined. Okay. So what about this case? When lambda, no, not lambda, when Hessian matrix, back to Hessian matrix. When Hessian matrix is not positive definite or negative definite, but Jacobian is 0, what happened to that point? Okay, back to our, where is it? This one, right? Okay, this one. You see that we have 4 extreme points, right? And 2 of them, one is minimum, yes, and one is maximum. What about other 2? When the let's see, the Hessian is not negative definite or positive definite, we call that point is Saddle point. Okay, and you see that because Jacobian is 0, that means, well, when we find the derivative in one direction, in both directions, they are both 0, but the property is different. Maybe while going in one dimension, it's in one direction, it's maximum, and the other direction is minimum. Okay, we call it Saddle point, like this. The stationary point is here, right? Extreme point is here. We go this way, this direction from C to D. We see that, oh, this point should be maximum then. However, when we go this direction from A to B, it's minimum, right? But actually, this point is neither minimum and maximum, okay? Because it's conflict between 2 directions, okay? Then it is Saddle point. Okay, any question from people in Zoom? Okay, let us visualize this problem. Which problem is it? This problem, sorry. We will use, you can play in your own computer. You can do it by yourself. GeoGebra, just one moment. World Wide Web dot GeoGebra. Yes, this one. Yeah, GeoGebra.org. Okay, /3D. Of course, you can explore because it can do many things, but I'm going to do 3D calculator. Okay, what I want to visualize is, let me go back to X1. No, not X1. X power 3. Power to 3 plus X. No, Y power to 3 plus 2x power to 2, okay? X squared. plus 4y square plus 6. Okay, we got this. I think it's let us change the the dimension. How to do it? Just one moment. Show plane, show grid. Yeah. Let's go down to 100. 100. Oh, where's our extreme point? Where's our extreme point? Just one moment. Oh, it's too look ugly. It's very close to 0. So it should be, no, don't go that far. Yeah, just 3 or 4. It's no, not enough. Just one moment. Okay. A bit darker. No. Maybe it's quite difficult to visualize it because there's not much different. But we see that we have a 1 point, which is a minimum point, should be around 0, 0, right? Here, around here in this. Yeah, around here, 0, 0. Okay, and the other point, the maximum point should be around here. Around here. Which is minus and minus, right? Yeah, somewhere around here. It's a maximum point. Okay. And over here and over here, around here and around here. certain point. Yeah, later you can do it by yourself. Any questions? Yes. You do in your computer. You have your computer. Do it yourself. It's that easier. geogebra.org/3D. No, this is 2D. Hey, here, the address .org, right? geogebra.org/3D. Yeah. Yeah. The animation. The animation. Movie. ไม่เพราะว่าถ้าทำรูปก็ต้องมีของ
ใช่ดูก่อนแต่ว่าไม่ต้องถ้าใช้เฉยเฉยต้องใช้เน็ตขายดาวถูกไหมแต่ถ้าอันนี้ต้องใช้เน็ตก็ติดหรือว่าที่แปดดาว
หัวได้ไหมเซตติ้ง So for this one, because we know that the extreme point, it's let me show you the extreme point again. Stop sharing and then no. You see that this problem, where's the extreme point? The extreme point is around here, right? From 0 to 0. Yeah, from 0. And the other point is 0 minus 8 over 3, right? So you see that X and Y is limited somewhere around 0, 0, right? So we cover from -5 to 5. for both X and Y, right? But for that, you have to calculate this by putting X and Y back into this equation and then calculate F. So you see the range of F from minimum and maximum, okay? Okay, so you can see, right? Though we have maximum and minimum, but here it's quite difficult to see, right? Because the slope here it's not that strong, okay? But if you zoom it, well, around here you see that maximum, no, minimum is around here, right? It just reached the minimum, local minimum, because once it reached the minimum, it's, well, the function increase a little bit and drop again, okay? And also this size around here. How do I know this? The maximum point is around here because I calculated already, right? It's negative something and negative something, right? So it should be around here. Okay, and you see that it's convex around here. Okay. How people in the Zoom? Are you with us? Or are you sleeping? All right, so we really enjoy using GeoGebra. Okay. Okay. Now it's time to play with, play with constraint, equality constraints. We really enjoy optimization of the unconstrained, right? Unconstrained optimization problem. But it's, of course, in practical application, in some case, if the constraint is too far away from the area you're going to, the area that the optimum point locate, of course, you can ignore those constraints, right? But equality constraint, you cannot ignore that, right? So now we consider the case of equality constraint. We have minimization problem, okay? We're going to minimize this objective function, fx, subject to the equality constraint, okay? Gj, okay? J can be as many as you want. However, remember that the dimension of dx, the dimension or the number of these variables must be larger than the number of equality constraint, okay? Let me repeat again that the number of variables, this variable must be larger than the number of constraints, equality constraints, sorry. Okay, must be equality constraint. Why? Because if you have too many, okay, if you have if the number of equality constraints is larger than the number of variables, the degree of freedom is negative. If the degree of freedom is negative, you cannot solve the problem, okay? And if the number of equality constraints is equals to the number of these variables, you use root finding. You use, it's solve. You have to solve the system of equations instead of optimization problem, right? Okay. For optimization problem, the number of these variable is larger than the number of equality constraint. Okay. So how to deal with equality constraint? The most simple one, if your equality constraint can be written as explicit function. What is explicit function? Explicit function means, well, you can write any decent variable as a function of other decent variables. For example, you have x1 to xn, and you can write x1 as a function of x2 to xn, okay? Or write x2 as a function of the rest, okay? I suggest you to use direct substitution. What does it mean? For example, we can write x1 as a function of x2 to xn, right? So we substitute all x1 with this function. It's just eliminate x1, right? Okay. That way, we reduce the number of equality constraint, and we reduce the number of decent variable at the same time. Okay. And of course, if you can write all variables, all equality constraint as explicit function, that is your, then you are lucky. Okay. Because you can eliminate all the equality constraint by just substitute everything. Okay. So this is straightforward. If you can do that, do it first. Okay. Direct substitution. If not, we have to find a way to handle the equality constraint. Okay. And that technique, it's we call it Lagrange method. Okay. And in order to understand what's the development of Lagrange method, I will show you how we develop the Lagrange method. Okay. You know that at the extreme point, a necessary condition for f to have minimum at x star, that at x star we have f x star, right? Okay. You know that the derivative at that point must be 0. Okay. Right. Previously we did that. Okay. The Jacobian is 0. That means, well, the derivative in each direction 0. Okay. So we can write df total differential. df is a change in x1 direction plus the change in x2 direction. Consider the case where we have only 2 dimension, okay, 2 dimension problem, and df must be 0, right, at that point. Okay. You move one direction, you have to compensate with other direction. Okay. df becomes 0 always. Okay. Because df is constant at that point. Okay. Okay. So, and we have constraint. We have g. Let's say we have only one constraint, g. Okay. And any change in x1 and x2, okay, must satisfy the constraint too. Okay. Right. Because this is equality constraint. That means, well, you move to any place, it's all right. The feasible region must move along function g. Okay. X star plus dx1, x1 star, okay, plus dx1, and x2 star plus dx2 must satisfy the equality constraint. Okay. That means, well, this constraint is whole, right? So if we write this function, this equality constraint, as we expand it using Taylor series, okay, we can use x1 star, x2 star as a fixed point, fixed point, right? Yes, fixed point. Okay. And we know that we don't actually, this one is only approximation because you have a linear term, right? This is linear term. Also, you need more term, which is nonlinear, right? But it's make, if we include those nonlinear term, it's make our system, it's too complicated. Okay, but if we consider only the linear term, that means we cannot move far away from the fixed point. Okay, we should work with the point around the fixed point. Okay, if it's close to fixed point, it's okay. This one is accurate. Okay, but anyway, this term, this function, the g function, no matter we write, we expand it using anything, Taylor series, but this function must be zero, always zero, must be whole, because this is our equality constraint. Okay, g must be zero. Okay, and what about g function at fixed point, at x star? It must be zero, right? This term also zero. This term also zero. Must be, right? Because that is a equality constraint. So if this term is zero and this is zero, right? So we have summation of these two terms. Okay, and well, it's too long to, this term, it's quite long to write, so we remove x1 star or x2 star here. We write just partial derivative of g respect to x1, okay, plus partial derivative of g respect to x2, okay. This one should be zero, okay. This is the deviation of dg, and deviation of dg must be zero, okay. Very simple. Yes. So this equation has to be satisfied, okay, must be whole for all feasible region, all admissible variations, okay. You change into any place, x1, x2 must hold this expression, this equation, okay. What does it mean? It means that, well, if we are at A, let's say A, okay, and this curve from P to Q is our G, our equality constraint. That means this expression we previously derived limit us to go along this direction only, along P to Q, along function G. It cannot leave the function G, because if we move x1, x2 must be compensated by the previous one, by the previous equation, right? It cannot arbitrarily move. Okay, so that means we cannot move from A to D. Okay, we move to the left hand side, we have to go along with this function, okay, which forces us to move along this G. Okay, so from this one, we write dx2 as a function of dx1. Okay, just the same equation, but we write dx2 as a function of dx1. Okay, yeah, we got this one, this equation. It tells us once we move x1, means, well, we change dx1. If dx1 is not zero, we have to compensate with dx2, this dx2. Okay, if we move from x star to any place, x2 must be moved by this dx2. Okay, and it's derived from derivative of g by x1 and derivative of g by x2. Okay. Okay. It's written here. This relation indicates that once the variation in x1 is chosen arbitrarily, the variation of in x2 is decided automatically. Okay. You got my point? For example, if we know equality constraint, for example, x1 plus x plus y must be 2. If, well, you put x1 1, you know, y must be 1, right? Because it's compensate that. Yeah. So we know the change of x2 by x1. So we put this equation back to this expression. Because we know df, how df change with dx1 and dx2, right? Now we know the change of dx2 is a function of dx1, right? So we substitute dx2 here with this expression, okay? And then you got this. What you got is df, of course, df is 0, right? And when we plug those dx2 in the original function, we get this one. The partial derivative of f respect to x1 minus this term, okay? Very long. It's difficult. It's complicated to read. Okay, so we use this one to define the local optimum point in case of constraint problem. Okay, this function, we reduce the form using only this. Okay, we obtain this. So this equation represents the necessary condition, okay, in order to have x star as an extreme point in the condition of in the what's it constraint problem, okay, because this one already includes constraint. Okay. Okay, so that is the background. So when you solve the problem using Lagrange method, you don't have to go to the what's it derive. You don't have to derive that equation. Okay, it's much more simple. Okay, so this method is we call it method of Lagrange multiplier. Okay, and it is a strategy for finding the local maximum or minimum of a function subject to equality constraint. Only equality constraint can be handled by using Lagrange multiplier. Okay, you cannot use Lagrange multiplier to handle inequality constraint. Okay, and a bit about history. Okay, it's developed by mathematician. Of course, must be mathematician. And what else? The concept is transform a constraint problem into a form of such that the derivative test of an unconstrained problem can still be used. What does it mean? It's very simple. The method is based on the transformation of constraint problem to unconstrained problem. Okay. By using Lagrange method, you transform constraint problem, objective function with constraint, equality constraint, into unconstrained problem. Okay, with different dimension, of course. And the Lagrange function is a reformulation of the original problem that results from the relationship between the gradient of a function and the constraint. It may be difficult to understand, to explain this one, but just very in a simple word, it's transform constraint problem into unconstrained problem. Okay. Okay. Consider this problem. You minimize 2y plus x2 plus x1. Okay, you can visualize it using GeoGebra. It looks like that. And the constraint is x square plus y square equal 1. Okay. Okay. Yeah, you can do it now. This tube is the red tube here. Yeah, I should point it in here. The red tube here is our constraint. Okay. The feasible region is only on the circumference. Okay, on the surface of this tube, because all the x and y must be satisfied by this equation: x squared plus y squared equal 1. Okay. And the surface, this blue surface, is our objective function. Okay. Of course, from visualization, you can see that because the feasible solution is only on the surface, right? And this surface is the objective function. If you want to maximize it, where is the maximum point? Yeah, around here, right? Around this area. Around this point. Okay? And the minimum points around here. Inside this. Okay, you can see from here. If I move it into 2 dimension, say x and y, and then the feasible region is only on this circumference of the circle. Okay. Yeah. And this is our maximum point, and this is our minimum point. Okay. Then the question is, how can we use the method of Lagrange multiplier to solve such a problem? As I mentioned to you that, consider this one. We are working on the 2-dimension problem, and we have one constraint. Okay, degree of freedom is 1, right? 2 minus 1, degree of freedom should be 1. And the necessary condition for existence of an extreme point change now, because we have constraint, right? We should use the expression we derived previously. This one, okay? I just copy and paste here, so you can check. So you see that we have derivative of f, which is our objective function, respect to by x1, right? And we subtract it by this term times with derivative of g by x1. You see that this is by x1 and this is also by x1, right? The only complicated thing is this term, the terms in front of derivative of g by x1, right? We change. Writing this way, it's too difficult to read, right? I change that term to just lambda. Okay, and I call that term as Lagrange multiplier. Okay, so we change the necessary condition to this function, this expression, derivative of f by x1 plus lambda times with derivative of g by x1. This term must be 0. Okay, from the necessary condition we derive a couple of minutes ago. Okay, And what else? Of course, x1 can be, it should be xi, right? x1 and x2, it's the same thing. Okay. So we have one more equation. Derivative of f by x2 plus lambda derivative of g by x2, right? Becomes 0. Okay, and the last one, derivative, no more derivative. Equality constraint must be whole. Okay. And you see that from this necessary condition, three condition, right? We can derive all these three conditions by just transforming or converting the original objective function fx1 x2 plus lambda gx1 x2. If we write this function, we call it Lagrange function. Okay. Okay. We call it Lagrange function. It is defined as the original objective function plus lambda, which is Lagrange multiplier, times with the constraint function. Okay. And you see that we have three variables, right? Already, right? Originally, we have x1, x2, right? But once we transform to Lagrange function, we have one more variable, lambda, which is Lagrange multiplier. Okay. Then if we find the derivative of Lagrange function by x1, we obtain this. We obtain this function. The second line, this function. And you see that this function is exactly matched with the necessary condition. Okay. Also, if we find the derivative of Lagrange function by x2, we obtain another necessary condition. Okay. And the last one, if we find the derivative of Lagrange multiplier, of Lagrange function by Lagrange multiplier, we obtain this condition, which is an equality constraint, which all of them match with necessary condition, right? Yes. So this is how we solve the problem. You don't have to derive it from the beginning. You transform original objective function and constraint to Lagrange function. Okay. Then derivative of the Lagrange function by each element and Lagrange multiplier, you get necessary condition to define the optimum point. No matter it's local minimum or local maximum, it must satisfy this. Okay. Okay. Now we solve our, if we want to solve this problem, we just formulate Lagrange function. Lagrange function is 2y plus x squared plus x, right? This from original objective function and plus lambda times with equality constraint. Okay. Okay, any questions? Any questions? So if you feel sleepy, you can, it's a good time to ask some questions. เราจะโซฟมันยังไงอะถ้ามีคอนดิชันไหนมีวิธีไหนในการ handle constraint ถ้ามัน direct substitute โอเคมันหายไปถูกไหมแต่ถ้ามันมี constraint อยู่แล้วจะโซฟมันยังไงอะไม่พอมันคืออะไรไม่เข้าใจคำว่าไม่พอ
คือเราจะทำอะไรนะอุ้ยอาจารย์มีคำถามมันถามว่า
yes and then kindly in the end of the class tell me about what okay okay I check your questions just one moment the date of midterm exam is the question yeah midterm exam is on October right October pardon 20 of October okay in the morning yeah 9 to 12คำถามเลยนะใช้เมื่อมี equality constraint
ที่ก็คือไอ้ที่สิ่งที่
subject to นี่ไง
มันมีแค่เหมือนมีแค่สมการเดียวคือไม่พอกับการ
ไม่คำถามคือโอเคปิดอันนี้ไม่มี equality constraint โตได้ไหมได้สิทำไมไม่ได้ล่ะมินิมัลนี่ก็หา extreme point ไงใช่ไหมไม่ใช่แต่ว่า point นั้นมันจะไม่ satisfy ไอ้ตัวนี้ไงเห็นไหม
พวกแบบนี้พวกแบบแค่หาสูตรแบบ
feasible region กำหนด feasible region แค่นี้
อันนี้เข้าใจ
ถ้าพอมันมีอันนี้ปุ๊บ condition เดิมใช้ไม่ได้เหตุผลเพราะ condition เดิมอ่ะมันไม่มีตัวไหนกำหนดเลยว่ามันต้องสอดคล้องกับอันนี้ถูกไหมจากโกเบียนเป็นศูนย์แล้วไงอ่ะมันไม่ได้บอกว่าที่จากโกเบียนเป็นศูนย์แล้วไอ้ตัวนี้จะ certify นี่อือฮึบังคับให้มันอยู่บน constraint นี้ So once you derive on these three conditions, you see that we have three variables and three conditions, right? Now we can solve the problem. It becomes system of equation and you can solve it. Using any tools, I don't know, but I cannot solve it. It's not linear. It's not easy to solve, right? But degree freedom is already zero. If you know, wow, you can use any root finding solver to solve it. Okay. Yeah. Our task already finished. We formulate that problem. Then the next task is solve it. Okay. But from visualization, see. From visualization, yeah, we know the result, right? But this one is okay because we're working with 2-dimension only. Yes, we work on 3-dimensional. I mean, 3 this variable, it's impossible to visualize it. Okay, so now you know the concept of Lagrange multiplier, right? How we apply Lagrange method of Lagrange multiplier to solve the constraint optimization problem. But that constraint must be equality constraint only. Okay. And I have few slides here. You can read by yourself. It's a definition. I mean the why is it? No, not this one. Sorry. Yeah, the meaning, interpretation of the Lagrange multiplier. What is the physical meaning of Lagrange multiplier? Okay. You can, well, you can read it your pace to understand it. All right, so I'm going to skip this because later you can read it by yourself. If you have any question, you can ask me later. All right, so now we move to inequality constraint. The equality constraint must be treated differently from equality constraint. Why? What is the difference between equality and inequality constraint? The equality constraint always binding, right? Always binding mean that the solution must be on that function always, right? However, in case of inequality constraint, we don't know. Maybe this constraint is not active. This inequality constraint is not active, right? If it's not active, then these signs lesser or equal becomes lesser, which is not involved in the in the objective function anymore, right? It does not define the optimum point. But if it's active, if it's binding, this relation becomes equal. That means it becomes an equality constraint, right? Okay. So we don't know actually. Yeah. We don't know beforehand that this constraint is active or not. Okay. So how we can solve this problem? The first technique is we can convert this inequality constraint to equality constraint by adding slack variable. Yj is slack variable. So once we add slack variable, okay, and it must be non-negative, right? Because this is lesser or equal, we cannot add negative value there. So gx plus yj square render this expression to equation, okay, become 0, right? Because you see that this is always lesser or equal, right? So if you add a small, no, maybe not small, a positive number there at the left hand side, this relationship becomes equal, okay? So we render the inequality to equality constraints. And once you have equality constraint, you know how to do it, right? You can use Lagrange multiplier to solve the problem. Okay? You see, once we transform the inequality constraint to equality constraint, this problem can be solved conveniently by method of Lagrange multipliers. By saying conveniently solve, it doesn't mean it's easy to solve. Okay, so I recommend other techniques. This technique called Kuhn-Tucker conditions. Okay, sometimes you say, well, not KT, it's a KKT, Courage-Kuhn-Tucker conditions. Okay, the same thing. Okay, so for this one, is more or less similar to Lagrange multiplier, but we need extra condition to handle the inequality constraint. Okay, we formulate the what's it, necessary condition this way. You see that look very similar to Lagrange multiplier, right? Okay, so what else we need? We need this condition. If mu is a KKT, okay, Coulomb-Tucker multiplier is mu. We need mu G become 0. What does this mean? This one is introduced by KKT condition. Okay. For Lagrange multiplier, you don't need mu G become 0. You just need these kind of things. Okay, with lambda. So you see that by analyzing this, how can mu G become 0? There are two ways. The first one, G becomes 0, G is 0, or mu is 0. Right? And what happens if G is 0? G is 0, that means the constraint, that inequality constraint is active, right? So we don't care about mu because G is active, right? Forcing that constraint to be equality constraint. Okay? If G is not 0, what happened? If G is not 0, mu must be 0. Right? In order to satisfy this condition. And if mu is 0, it does not contribute to the necessary condition at all, right? Because mu is 0, this term will become 0, right? Okay? That means that condition, that inequality constraint is not active. So it does not contribute to the what is it? To determine the optimum point, right? Okay, so now you know the trick, the KKT condition. We're going to apply all these things to the example, to the problem. I show you here. This is inequality constraint. We have only one inequality constraint. Okay, we want to maximize the objective function, which is minus x squared minus y squared. And the constraint is x plus y minus 1 must be greater or equal 0. Okay. So what is the Lagrange function? Our Lagrange function is, we call Lagrange function the same. Even it is inequality constraint, but we call it Lagrange function. Our Lagrange function is minus x squared minus y squared plus mu x plus y minus 1. Okay. We use mu here because, well, to remind ourselves that this is from inequality constraint. Okay. If it is equality constraint, we use lambda, right? Lagrange multiplier. But this one is KKT. So the condition, the necessary condition we have here is, well, derivative of Lagrange by x and derivative of Lagrange by y. Okay. So we have the first condition is minus 2x plus mu becomes 0. And the second one, minus 2y plus mu becomes 0, right? Okay. So from these two equations, we can derive x as a function of mu and also y as a function of mu. Okay. Okay. And the next one is our primal feasibility. Yes, we keep it here. No, Okay, later we're going to test it, but we're not going to use it now. What we're going to use it is complementary slackness. Every time we deal with inequality constraint, the KKT condition comes with complementary slackness, right? Mu G must be 0. This mu and this is G. Our G is x plus y minus 1. Okay. So mu times it, x plus y minus 1, it's 0. Okay. So by analyze this complementary slackness, we have two ways. Okay. Either mu is 0 or x plus y minus 1 is 0. Okay. Two choice. And if mu is 0, of course, previously we derived x and y as a function of mu. You know x and y. Okay. X is 0, y is 0. Okay. Good. So we can test it with primal feasibility. Our primal feasibility is our inequality constraint is x plus y minus 1 must be greater or equal 0. Yes, we test it, but it's failed. The primal feasibility, okay? That means this condition is not satisfied, okay? This is not the solution. What about the second choice? It is x plus y minus 1 is 0, right? So we substitute x and y, okay? Then we get mu is 1, right? Once mu is 1, we know x and y, right? It's 0.5, 0.5. And we test it with primal feasibility. Yes, it is. Then the condition is satisfied. And this is our solution. Okay, so for this problem, of course, you can visualize it using GeoGebra. Okay. Okay, you can do it by yourself later. The next example. Okay, we maximize xy. This is our objective function. And the constraint, we have both equality and inequality constraint. The first one, equality constraint is x plus 2y minus 3 is 0. Okay. And the inequality constraint is x minus y is greater than or equal 0. Okay. Again, to solve this problem, we use KKT, right? The first thing to do is we formulate the Lagrange function, and the Lagrange function consists of 3 terms. The first term is from objective function directly. Okay. The second term from equality constraint, right? Okay. In front of this term is lambda. Lambda is a Lagrange multiplier. Okay. The third term from inequality constraint. Okay. And you have to term it with mu. Okay. What is mu? Mu is KKT, right? Okay, so for stationary, the necessary condition is we find the derivative, partial derivative, respect to x, okay? And the second one is derivative of Lagrange respect to y, okay? So we get what do we get? Y plus lambda. Right, lambda. Okay, other term becomes 0, right? Plus mu. Okay. And so we rearrange this one. We get y is minus lambda minus mu. Okay. And the second necessary condition is x plus 2 lambda minus mu, it's 0. Okay. So we rearrange it to obtain x. X is minus 2 lambda plus mu. Okay. So we keep prime of feasibility here, but we are not going to use it now. And of course, to our feasibility, mu must be greater than or equal 0. And we analyze the complementary slackness. Complementary slackness is mu g, right? Mu g must be 0. So our g is x minus y. Is it correct? Right. X minus y. So mu times with x minus y must be 0. Okay. So mu can be 0 or x minus y is 0. Okay. If mu is 0, then how to solve it? Come on. Yeah, mu is 0. You see, y is minus lambda. Here, x is minus 2 lambda, right? And we have equality constraint, one equality constraint here. So we have x, y is a function of lambda, x is function of lambda. We substitute it. So we have one variable, which is lambda, right? So we can solve for lambda. And once we obtain lambda, we substitute lambda here and mu here back. We obtain y and x. Okay. Or x minus y is 0. If x minus y is 0, then, well, you know, x and y, right? You substitute x and y here. Okay. We obtain lambda equals to mu. Okay. And with this one, lambda equal to mu. And this one we derive from equality constraint here. So with these two equations, we can solve the problem. We can solve for lambda and mu. Okay, and substitute back. We obtain y and x. Okay, in this case, y is 1 and x is 1. Okay, so two choice, right? We have 2 points. We have to test for primal feasibility. Okay, and both are satisfied, right? Okay, the primal feasibility are satisfied. So both points satisfying the KKT condition, okay, can be solution for both. But now you have to check whether which one has, you're going to minimize or maximize. If maximize, you go with this one. If minimize, this one, okay. Okay, this is how you can visualize it by yourself, this one. Okay, any questions? We still have one topic left. It's convexity. But convexity is quite simple. Yes. Example 1. Yes. Ah, yes, yes, yes. You need Hessian. You need sufficient condition. Because the necessary condition only tell the what's it? It's analogous to necessary condition. Okay. Okay. The next one is convexity. Okay. So from this topic, you will learn the beauty of convexity. Okay. Actually, the convexity is fascinating mathematical concept. It's convex, of course. Do you know the convex and concave? Convex is it's what about concave? Concave is different way. So convexity is a property of set points. Okay, where if you have set one set, then you choose any 2 points in that set, and you draw a line between 2 selected points. All the points in that line belong to the original set always. Okay, that set it's called convex set. Okay, and if there are even only 2 points that you draw a line and part of the line violates that set, that means part of the lines is out of the original set, we call it concave set or non-convex set. Okay. So convexity is fundamental concept for optimization. Okay. So if we later you will learn more why we need the property of convexity first. For example, this one, this is a, it should be, you can draw a line here or it can be a circle. On this set, you choose any 2 points in this set and draw a line. You see that line belong to the set. Okay. But on the right hand side is non-convex set. You see this area. If you choose this point and this point, you see, if we draw a line, part of this line, okay, a point in this line do not belong to that set anymore, right? So it is non-convex set. What else? The first thing you learn is convex set, okay? And the second thing is convex function. For convex function, concept is quite similar, but it's defined different way. It is function only. For convex function, if f is convex function, the linear interpolant between any 2 points in the set always greater, okay, than the function, the value of the function. Okay. So we call this set, this function, sorry, not set, this function is a convex function. Okay. If the interpolant this green line is interpolant. Okay, we interpolate 2 points here. Okay, we vary alpha. Okay, if alpha is 0, then it should be this point, right? If alpha is 1, it should be this point. Okay, and when alpha is between 0 and 1, all this point along this way. Okay, but all point, any alpha, you get the green, the value of the function, the interpolant is higher, is above the f, okay, the function. Okay, so this function is convex. What about concave? The opposite way. When the function is go this way, yeah. Okay. Okay, one thing. Why do we have to consider the convexity? If we know that in this region is a convex set, it is a convex function in this region. What do we know? It interprets that in this region we have only one, it's a monotonic. Okay, if we define this region as a convex function, we can have only one minima. Okay, we cannot have both minimum or maximum in that region. Okay, so this is a very important property. Okay, so what else do we need to learn about convex set? The intersection of convex set is always convex set. That means, well, if you define one region as a convex set and another region also convex set, the intersect of them must be convex set, not union, just intersect. Okay, and also, well, we have a property on a convex combination also. And the last one is the convex hull. The convex hull, what is the convex hull? Convex hull is a set, no matter the original set is non-convex, but if we take convex hull, it becomes convex. Okay, the smallest convex set that can contain the set we consider. Okay, we call it convex hull. Okay, now we have more example of convex set. Okay, we have two concepts, right? Convex set and convex function. All right, so for convex set, this is, you think this one is convex set or not? Yes, it should be convex, right? How about sphere? Sphere also convex. This one? Yes. Even polygon also convex set. So if we have, for example, if our feasible domain, feasible space is a convex set, we guarantee that along the way, we will not leave the feasible region anymore. Okay? Because we cannot leave it because, well, if we follow the method properly, okay? Because along the way, it will not leave the convex set. Okay, this is convex function, right? This is convex function, this is concave function. Okay, example of it. To test it, how to test the convex function and concave function? One way is use interpolant, right? Or you can use a second derivative test, okay? Because a second derivative test give you information regarding minimum and maximum, right? And for this one, you get convex, you get minimum point, right? For concave, you get maximum point. Okay? And one important thing is the optimization problem is called convex programming. You see, many solver guarantee that it's designed for convex optimization problem or convex programming. What is convex programming? What is convex optimization problem? For convex optimization problem, must be convex. Okay. The objective function must be convex function. And the region, feasible region formed by the constraint must be convex set. Okay. Then if you test your problem that the feasible region is convex set and the objective function is convex function, then you can use that solver. Okay. The solver designed for convex programming. Okay. And if convex, the fx is convex if the Hessian metric is positive semi-definite or minimum. Okay. Yeah. All right. So this example, we have fx is x cubed minus 3x squared plus 2x. Then determine if it is convex on the domain R, a real number. Okay. Domain R, of course, R is convex because it's cover everything, right? It should be convex set. And we test by using second order derivative. Okay. This is first order, and the next one is second order. And you see that the second order is positive when x is greater than 1, right? So it's convex. From this part, okay, when x is greater than 1, this is convex set. No, this part is convex function, but this part, when x is less than 1, the function is concave. Okay. So if you want to use convex programming to solve this problem, you must limit your space to be greater than 1. Okay. Okay. Then, well, this problem you can do it by yourself later. Plot the contours of the following function. Yes, this function and this function, and identifying the optimum point. Okay, by using GeoGebra, it's all right. And the next one is solve the following problem. Yes, we have objective function and one constraint, equality constraint. How to solve this problem? Yes, Lagrange, using Lagrange. And the next one is solve the following problems. The minimize x1 minus x2. Okay, we have one constraint, inequality constraint here. Okay, yeah, KKT. This one also use KKT. Okay, solve this subject to this constraint. Okay, so finish. No, we have more. Yeah, this one, you have multiple. KKT, of course. Yeah, and it's quite difficult for this one. It's quite difficult. Mhm. Yeah, it is done. Oh, sorry, you asked for changing the date for exam? No, sorry. Yeah, it's unchangeable. Okay, any more questions? I think, well, last week, everyone was on site, right? Okay, any questions? If not, let us call a day. Huh? Okay? Okay, so people online, so enjoy the rest of the day. Okay? We finished. Okay, let's call a day.